Hi, I am Lionel Parreaux, and I will present this paper on multi-stage programming in the large with stage classes. I would like to start by contrasting two existing approaches to high-performance programming, namely multi-stage programming, or MSP for short, and template metaprogramming. Multi-stage programming offers the ability to specialize or partially evaluate programs in a type-safe and modular way using the expressive abstraction capabilities provided by a general-purpose programming language. This is in stark contrast with C++ template metaprogramming, another common approach to program specialization. C++ templates are also quite powerful, but they rely on a relatively obscure and inflexible untyped meta-language, making their use for metaprogramming unnecessarily challenging. Yet, despite their obvious drawbacks, C++ templates have enjoyed a colossal success in industry, while multi-stage programming has been mostly relegated to niche applications and academia. But why is that? There are many reasons that could explain this state of affairs. In our paper, we argue that one important reason is that multi-stage programming only tackles one part of the modularity problem. While it provides tools for modularizing the program generation side of a metaprogram, it does not provide tools for making the generated program itself modular. Indeed, traditional staging only deals with generating expressions, making it great for generating highly efficient algorithmic kernels such as individual database queries, parsers, stream processing pipelines, linear algebra computations, etc. However, it provides no dedicated facilities for generating shared data structure, class, or module definitions. It usually has limited capabilities for sharing code across function definitions, which hampers its use for generating more comprehensive programs which share and reuse generated components. Moreover, code generated by multi-stage programming is akin to a black box with limited interactions with outside code. By contrast, in C++, the code generated by template metaprogramming is seamlessly embedded within the host application and retains its modular class-based design. In particular, template-generated code can still interact with the surrounding code through rich interfaces. So, can we combine the advantages of both approaches? We introduce stage classes, a new statically typed abstraction that extends multi-stage programming by enabling the manipulation of object-oriented class definitions, while ensuring that the generated code is well-typed and well-scoped, in line with the guarantees offered by traditional multi-stage programming. We say that this approach enables full modularity, which we define as the property of a program generation system which allows both the program generation code and the generated program code to be modular and shared. We argue that this unleashes the potential of multi-stage programming, making it a practical tool for structuring program generation in the large, at the scale of real-world applications. We advocate two main usage modes for stage classes. First, as a way of defining generic libraries that do not pay for their genericity, whereby individual users directly use the generated classes specialized for their use cases. Second, as a way of taking multi-stage programming to the next level by allowing the generation of class and module declarations containing mutually recursive definitions. In the rest of this presentation, we will review the basics of multi-stage programming in Scala using the Squid framework. Then we will discover stage classes through a generic vector class example. And finally, we will briefly describe two stage class application examples. Squid is a type-safe metaprogramming and extensible compilation framework implemented as a library in the Scala programming language. It is open source and available on GitHub. Squid generalizes the multi-stage programming discipline in several directions, such as supporting pattern matching on program fragments. This presentation is about how Squid generalizes MSP by supporting the manipulation of class definitions. One of the main mechanisms of Squid is Quasiquotation, whereby one can construct program fragments internally represented as abstract syntax trees. One can compose these program fragments together programmatically by using the $sign, which allows us to escape quotations and insert existing program fragments inside bigger program fragments. A program fragment in Squid has type code of some type in some context, which reflect the type of the term being represented and its scope dependencies. For instance, the value C0 has type code of int in the empty context, as it does not contain any free variables. Program fragments can then be runtime compiled and executed with the run command. Finally, Squid keeps track of the context dependencies of each program fragment, so as to statically prevent the occurrence of scope errors in generated programs. We now go over the basic functionalities of stage classes with a simple example, the staging of a class for representing numerical vectors. The following plain Scala class represents a vector of 3 immutable floating point coordinates. We define a derived field, sum, which holds the sum of the components, as well as 2 methods, prod and equals, which compute some result given another instance of the class. Several properties are hard-coded in this definition, namely the arity of the vector, the type of the elements, and the implementation structure of each method. Our problem is that generalizing any of these aspects normally incurs significant runtime overhead due to the cost of abstraction. Let us now have a look at how one would define the same vector3 class but through the stage class interface. A stage class is an instance of the Squid class called class. Notice that we are now defining an object called vector3, which is no longer an actual class. The parameters of our stage class are now defined using the param method, which uses side effects to register the corresponding parameters in the enclosing stage class instance. Similarly, fields and methods are defined with corresponding virtualized constructs. Notice that their bodies are now given as program fragments. In a stage class, self refers to the type of the class being defined. One can call the GenerateCode method on this stage class instance, which will generate the code of a class which is equivalent to the original unstaged vector3 class we saw before. The first thing that this new class representation allows us to do is to add staging time abstractions to facilitate the definition of its methods. Here, we remove the redundancy present in the implementations of prod and equals by defining a fold combinator to perform some merging and reduction on the components of the current vector and a vector argument. This combinator allows us to define prod and equals more simply as follows. Note that Squid will automatically reduce the lambdas involved in this exercise. Abstractions such as fold are zero cost in the sense that they only exist during code generation, the resulting generated class code retaining no trace of them. Next, we want to generalize the arity of the vector class. This can be done by parameterizing our stage class instance with an integer n, which requires that we make our definition a class again, as objects in Scala cannot be parameterized. The fields of our stage class are now defined programmatically by filling a list of n calls to the param method, and the implementation of fold and sum are updated accordingly. Interestingly, the implementation of prod and equals remain unchanged, as they have already been abstracted. Again, a call to generate code, when constructing the stage class instance with the appropriate argument, yields the same class as before. Finally, we can further generalize our stage class by making it generic over the element type. Note that we are making the stage class generic, but not the generated class, which means that our changes will incur no runtime cost whatsoever, despite the fact that generics on the Java virtual machine are erased. In order to handle the generic type n in our stage class, we need to add an implicit parameter which reifies the representation of the element type n. This parameter will be synthesized by Squid automatically. Moreover, we need a second implicit parameter for witnessing the fact that n is a numeric type. The implementation details of this version of the staged vector class can be found in full in the paper. Before we conclude this presentation of staged classes, note that we can naturally define specialized methods by simply using parameters outside of the code quasi-quotes. In this example, a new specialized method is generated every time the method bar is called. In this context, it is crucial to cache generated methods which share the same specialization arguments, so as to avoid code duplication and to prevent infinite recursion on cyclic specializations. Caching is done using the cached annotation. This is similar to template metaprogramming in C++, but with the full power and flexibility of multi-stage programming, allowing programmers to easily define arbitrarily complex metaprogramming constructs. As the first application example for stage classes, we consider the design of type-safe type providers. Type providers are metaprograms which generate ad hoc type representations reflecting the structure of some sample data obtained from a given data source. For instance, we may define a CSV provider whose goal is to construct a type reflecting the data present in a given CSV file. In this example, we use CSV provider to create a type representing persons, and we use it to load data from an additional row provided to the generated read method. What we mean by type-safe in this context is a stronger notion than usual. Not only are the generated type implementations checked by the host language, but they are in fact guaranteed to be well typed by construction of CSV provider itself. This means that as long as our implementation of CSV provider type checks, we can be sure that it will only generate type implementations which themselves type check. The next use case we consider is a staged database system compiler. We start from some SQL table definitions and generate container classes specialized for storing the corresponding data. We use Squid to runtime compile these classes to executable code. In the next phase, we receive queries in SQL format, such as insertions, deletions, and analytical queries. We generate specialized classes for executing these queries as efficiently as possible, accessing the previously mentioned specialized data containers efficiently, with abstraction overhead removed by the staging process. These query execution classes are finally themselves compiled into executable code, after which we can execute our database queries without any interpretation overhead. This approach is truly multi-stage. It relies on successive stages of compilation, which correspond to different phases at which more information becomes available at runtime. It is interesting to compare this approach to the way existing staged query compilers have been designed in previous work. In these existing approaches, the entire database infrastructure is usually generated and compiled for each independent query, which makes for impressive single query benchmark results, but does not scale to real data management use cases. In conclusion, staged classes aim to bridge the gap between two established metaprogramming techniques, multi-stage programming and template metaprogramming. The goal is to obtain a system which is more practical than MSP, but also more principled and expressive than template metaprogramming. This approach is implemented in Squid, currently as a prototype which lives in a private branch of the repository, but soon to be open sourced. Thank you for watching.